taking 20 meters. Welcome to the YCARS July presentation meeting. Tonight we have a very special guest. He is an international man of mystery. The ham radio operator and YouTube entrepreneur, the Smokin Ape, joins us this evening. His channel is one of the more technical mentoring channels on YouTube. He is also part of the Coffee and Ham Radio's channel. He brings the science to a level that all of us can understand, and tonight he's here to help us understand baluns, UnUns, and chokes. So welcome, Ape.
But no, thanks for having me. I'm really excited to be here. I'm pretty informal, and I think I have that one of the slides. So if anybody has any questions, just feel free to ask them whenever. And I really framed the presentation as really more of a conversation than a bunch of slides with a bunch of words. What I was going to do is just show some examples of some different things and talk about them a little bit to really just have a conversation with everybody. I don't really necessarily like the whole, hey, I'm lecturing at somebody. I'd rather talk with folks and show them some of the stuff that I've done and maybe hear a little bit about what they're doing. I don't fancy myself as an expert or some big time person. I'm just a regular person like everybody else. And some things I know and some things I don't, but I'll be totally open and honest about it. And that's about it. You want me to share the content? I can't hear anybody, so I'm just going to go.
I'm muted. I said I can share it if you want me to, or if you're comfortable.
No,
doing it.
I got it.
Okay. Cool.
Actually, I think what I'm going to do is go over here and do this. Can everybody see that? Okay.
Yeah.
Awesome. So that's the title page, and now I want to pull that window up. Let me go down to the next slide. So I just wanted to do a quick intro. Like sometimes hams will get a little upset because I go by the Smokin Ape, and I'm just a ham, but I'm really more of a fan of RF in general. So way before I was a ham, I was into like public works scanning with like scanners and stuff like that. Did a little bit of stuff with shortwave and did stuff with SDRs. Really was into playing around with SDRs for some reason. I just liked it. And then kind of on a fluke thing, one of my buddies bought some Baofeng radios and was telling me all about, hey, we can become ham radio people. And I didn't know that was a thing that you could do. I still thought there was like all these difficult tests to pass, and you had to do code and stuff, and you didn't. So we just went and got tested and passed. If folks don't know, I do have a YouTube channel. Some people watch it for some reason. It seems to be popular in certain crowds and then maybe not so popular in other ones. But as John was saying, what I really try to do is do a lot more technical stuff at a beginner level. Just given that with amateur radio, there's kind of an expectation that hams can work on and modify their own equipment, and we're kind of really responsible for the way that we operate. And so I do tests where we look at spurious emissions on things, or how you can make sure that your antenna is working correctly. And I really try to do a lot of DIY stuff. I don't want to hate on antenna manufacturers. We actually, as part of Coffee and Ham Radios, actually do the design work for a lot of the antennas that we sell. They're antenna kits, but they're all DIY kits that folks put together. A lot of the big antenna companies, and I really don't work with them very much. They charge a lot of money for antennas that maybe are suboptimal. And with a little bit of time and ingenuity and some basic tools, anybody can build them. And so I kind of try to do that on my channel to just make amateur radio a little bit more approachable to folks. When I started doing YouTube stuff, I just named my channel the Smokin Ape. It was a long time nickname and screen name that I would use like on forums and stuff like that. And that's just what I go by as Ape. Like tons of people call me that, friends, my neighbors, everybody. So it might seem a little weird to you, but it's not weird to me. So just call me Ape. And I think I mentioned I'm pretty casual. So, again, I'd rather just have more of a conversation with everybody than some kind of formal lecture, if that's okay. So getting in the content, when I became a ham, I was a technician for a long time. And then when I got into being a general in the world of HF, I wanted to get an antenna up. And I looked at the prices and I was like, man, I don't know. It seems like it's pretty expensive. So I went down the path of trying to build something. And what I was seeing is that you needed to have a Balun on your dipole. And there seemed like there was a lot of people who were like, you don't need a Balun, don't do it. But a lot of the folks that I really liked, like pretty nerdy guy, Stan Jubilisco is like one of my favorite YouTubers of all time. Um, and there was another guy, Randy K, I think it's K7AGE. He did a video where was building a dipole and they were talking about balance. And so it took me forever to figure out what the heck a Balun was and how it worked and how you could build one and why you would even want one. And so what I did on my channel, I do a lot of work with chokes and baluns and transformers and stuff like that. And it's really kind of rewarding because a lot of people are like, "Hey, I built my antenna. It was my first one based off your video, and it was really awesome." But the thing is that what I have in here is that there's lots of inconsistent lexicon that litter the language of ham radio, and we have all these words that mean the same thing, and then we have the same word for many different things, and it's just really confusing. And those are chokes, baluns, choke baluns, transformers, transmission line transformers, matchbox, matching units, impedance transformers, and UnUns. And they're all kind of related. I guess you could make an argument that a choke is not a transformer and shouldn't be called a transformer. But for me, I think it's just really important for folks to understand what the thing is and how it works and not worry about the words or the language because there's so much inconsistent language that gets applied to these things. As long as you understand what they do and how they work, you can improve your amateur radio experience. So I thought I would start off by just talking a little bit about common mode current and the whole Balun thing. And so many of you probably have already seen this and are familiar with it. But this is a diagram that the league published. And it really just talks a little bit about the problem with common mode current. And, I get into conversations with hams all the time that say, common mode current's fake or it's not a problem. Or if you try to stop it, you lose your signal. And I just think it's a little bit silly. But what we have here is that you have the two arms of the dipole. Arm one is on the left, arm two is on the right. And then you can see what's called differential mode current. And differential mode current is current that runs in equal and opposite directions through a transmission line. And the problem that you have is that with ground currents, they look for ground and they're going to take the least impedance, the lowest impedance path to ground. And what we see on the right-hand side is a little arrow pointing this as common mode current is that this stuff will go down the outside of the shield on your coaxial cable. And a lot of folks will say, well, why is this a problem or why would I worry about it? If your dipole or any other antenna is mounted in a way that your transmission line is not perpendicular to your antenna element, your transmission line actually turns into an element, a radiator of its own, and will cause interference and potentially noise that worsen your signal to noise ratio, which is something that we don't want as hams. You obviously want the best signal to noise ratio you can get so you can understand what people are saying when you're trying to make a contact. The other thing is that this common mode current, it's looking for a path to ground. So it comes into your shack searching for that path. And you hear stories of people touching the chassis of their radio and getting a shock or touching their microphone with their lips and getting a shock. But one of the problems that I was really having before I really knew how to kind of bust the common mode current problem is I do a lot of FT8 and my computer would freeze up when I would transmit. And I would get this error message saying that my rig control failed. And I couldn't figure it out. I just thought that my laptop was no good or the PC that I was using was no good. And what I came to realize is that common mode current, while I was searching for that path to ground, was coming in through my radio and then coming through connections to my radio, including my USB cable. And then it was causing my computer to freeze. And so one of the first things I did was make sure I always had a good choke or a choke balun at my antenna feed point, and then I would also put one at my antenna tuner. So that way, if any common mode current made it past the first choke, then the second one should stop it. And I also put them on all the cables. And we'll look at a diagram of that. But what happened is that my noise floor went from like an S5 to 7 to like an S1.5 to 3 in most cases. And my equipment stopped failing. And I was really happy with that. So even if you do lose a little bit of efficiency by using chokes and balance and stuff like that. I was able to operate, and I was able to operate better than I could before, and so I was really, really happy about it. So I wanted to put this picture in here and just talk a little bit about some of the problems, just in case somebody had questions about it. So when you look at coaxial cable, you really do have three conductors. So one of the things that's unique about RF is it travels on the outside of a conductor. So a lot of times the bigger the conductor, the more RF that you can get passing through that conductor because there's more surface area. But when you take a look at the shield, which is kind of like that wire mesh that's on the outside. So in the center, you have the center conductor, which is solid core copper in this case. Then you have some plastic. So sometimes it's Teflon, but sometimes it's foam. It can be all kinds of things. Is some dielectric that's wrapped in foil, and then on the outside of that foil, you have what's called the braid. And that braid, the RF can travel on the inside of that braid and on the outside of the braid. When you're talking about differential mode current, which is the good current that we want, it travels on the inside of the braid. The common mode current travels on the outside of the braid. And what happens is that common mode current gets reflected. Reflect is not the right word. Returned from the antenna connection because it's looking for that low impedance path to ground. And what happens is that your current becomes unbalanced on your coaxial cable. And that's why they'll call that an unbalanced transmission line. So what I have here is just a couple pictures of some stuff, right? So we have pictures of chokes, baluns, and choke baluns. And people get upset at me on my channel because I'll refer to these things as baluns, I'll refer to them as chokes, and I'll refer to them as choked baluns. And one of the things that comes up all the time is that these are mostly UnUns because the the connectors are for unbalanced coaxial cable. So these must be UnUns and not baluns. And maybe they're chokes and not really a balun. And again, I don't really care about any of that. What I do care about is that so the two at the top part of it, you see some coaxial cable. That's RG58, and I think it's about 11 turns on there. Around a T240 toroid, and it's a mix 31. We'll talk more about toroid composition and size as we go on. But really what those do is they create a magnetic force around that toroid when current passes through that coaxial cable that attenuates that common mode current. And we'll look at why that works. But on the high side, I paid $15 for each of those I call them toroids. So I think legitimately they're called toroids, but toroid sounds a little easier for me to pronounce. So they're about $15, and it's about probably a $5 to $6 piece of coaxial cable. So I was able to build those things for around $20 to $25. And when you look at commercially produced baluns, they're significantly more expensive than that. And I've tested commercial ones. I've tested the ones that I built, and the ones with the RG58 wrapped around them like that work exceptionally well. The one in the middle is another T240 mix 31 ferrite toroid. And what I have on there is 18 gauge Teflon coated. It's copper wire with a silver shield on there. And it actually has two bifilar windings, one on the left side, one on the right side. And so when you look at that, the bifilar windings create an impedance of around 50 ohms, depending upon how far apart the wires are from each other. In this case, it's about 50 on each side. So it's really about 100 ohms device, but you're splitting that. So it presents itself as a 50 ohm transmission line. And that one works really, really well. It generates a ton of choking impedance. On the bottom is a commercially available, what I would call a choke. I wouldn't call it a balun. And it's really just a piece of short coax, and it has ferrite beads on there. Now, because it's commercial, I don't know what those are, but that type, you can build them yourself, but they're very good for portable situations because they're small and they're streamlined. You can connect it right to your coax and still wind your coax up. But I just wanted to show a couple of examples there so folks would kind of know what I was talking about. The ones with the coaxial cable, they work really well for putting at antenna feed points. The one in the upper right-hand corner, that one I actually connect to the back of my antenna tuner. So right as it goes in there, I do have some choking that takes place. I can't see the Zoom screen because I'm looking at my screen. So if there's anything that pops up a question or anything like that. I can't see it. So John, you'll have to be a bro and help me out there.
Yeah, if if anybody has questions, you can pop them into chat, or you can go ahead and just unmute and ask the question. It's no problem at all.
This is actually a picture of one of the first chokes that I made, and I think this is RG8X. It was like a 6 or 8 foot piece of it or something like that. And I just coiled it up, and I was talking earlier about maybe I didn't talk about it, but a lot of people will make things called an ugly balun, and they do that by coiling coaxial cable up. And the problem with those ugly baluns is that they have to be tuned to a particular frequency, and they have a very high Q, and as a result, they're very narrow banded. So the ugly baluns, which is coiled coaxial cable, can work well for you at a particular frequency. They don't work well if you're looking to work a large swath of bandwidth. And then where it really becomes a problem, like I'm a greedy ham. Like I put an antenna up, I want it to be multi-banded. I want to be able to get wide bandwidth on it. I want to operate 10, 20, 15, all the bands. So for somebody like me, the ugly balun is just a really poor choice. Unless I want to have a bunch of them, I guess, and have an antenna switch or something like that.
Well,
But
with the ugly balun, isn't it affected by its surroundings much more than a wound toroid?
yeah, it is my understanding of it is that the magnetic field that it generates is like more fragile is probably the right way to say that. But what we have here is each one of those blocks has a clamp on toroid or ferrite bead, and and I think I have about 2 passes in each one of those. So that technically gave me 8 turns. But when I built this, I like to give things fancy names, and I was like, "This is my CMC Busta," and I used it for a while, and I don't use it anymore. I don't even know where it is, but I found a picture when I was putting together a presentation. So something like this is pretty easy to build. Everybody can do it, and it doesn't require any tools or anything like that. And this is the one of the early baluns that I built. It's terrible. I shouldn't even show it. Everybody be like, "This guy's a clown," but this is a 3D printed dipole center, and it was actually published on Thingsverse, is where you can get 3D open source files. Kevin Laughlin from, I think he's the old tech guy. He's down in Arizona living in a camper van right now, but I think he's from Michigan. He's a pretty popular YouTube ham, and he published the dipole frame, and I was like, yeah, I'm going to print that out and make a dipole. And this is like I said, it's terrible. This is actually speaker wire that I wrapped around a smaller toroid, is T140 43, and so it's not the right mix. You can use mix 43, but 31's better. And I just built this thing, and to my amazement, it worked really, really well. So if you have a 3D printer, you can start putting your own antenna stuff together relatively cheap. And I think those toroids are less than $5 a piece. And then, I'm sure everybody's got a pretty healthy parts bin. I had the ring connectors and the shrink wrap and all that stuff already in my toolbox. So it was pretty fun build, and I learned a lot doing it. But I think the point is that no matter where you are in your, I guess, antenna building journey or something like that, what I would say is don't be afraid to experiment and try. And even though this is not the textbook way to do something, I was able to put it together. I was able to learn. I was able to get experience. And the most important thing is I was able to have some fun. So I just threw that one in there. One of the things I wanted to talk a little bit about is testing stuff. And that's something that I do a lot on my channel is I test stuff. But in this particular case, what I was trying to do is test the SWR or the see if this toroid was, or this balun was putting any unnecessary impedance or causing an SWR problem for me. So I'm a big fan of the Nano VNA. I don't know how the club feels about them. I know that sometimes there's a holy war conversation between Nano VNAs and Brig Experts and MFJs and all that other stuff. But when I started building antennas, I wanted to be able to do I see you, Dan, do some analysis, and I wanted to learn stuff. And this Nano VNA had just really come out, and so I bought one. It was like $45. And I was like, why wouldn't I buy that, when the other devices are, two, three, 400, $500 in some cases. And when I got it, I take it out of the box and I look at it, and it was so demotivating because it's kind of complex and there's a lot of stuff on the screen, and I really didn't know what I was doing. And so I actually have tons and tons of videos showing how to use these things. If you're interested, you can check them out. And what I kind of committed myself to doing was is saying, hey, I'm going to use this lower cost approachable equipment that actually gives you tons of information besides just SWR, and make all these videos on how to use it. And because there was nothing like that when I first got mine, and it took a lot of head scratching and aggravation to figure out how to use it. But it's been one of the most valuable purchases I've ever made in amateur radio. But what we're just doing here is a simple S11 reflection measurement from the device through the toroid and into a 50 ohm dummy load. And I'll do that just to make sure that I don't have any problems with the toroid or wrapping. Some of the feedback that I'll get around these is that you're not supposed to bend your coax, and you're not supposed to bend your coax. And you can see here my coax is clearly bent. Bending coax it's terrible, right? But it's not so bad if it stays stationary. The real problem that you get is that your center conductor can work its way through that foam dielectric that we were looking at earlier. And the more you bend your coax back and forth, the worse that situation or problem can become. In any event that this thing goes bad and I start to have problems, I'll just buy another $5 piece of coax. It's not that big of a deal. So I wanted to put this definition in here, just to really kind of highlight some of the challenges that we have around the lexicon. And, people, like I said, get upset when you call something a device that they traditionally don't call it. Really, instead of having a valuable conversation around what the device does. So I actually did a video on this, and it says that it's useful to begin with terminology. It begins with the terminology of this important topic, and the term balun applies to any device that transfers differential mode signals between a balanced system and a balanced system and an unbalanced one, while maintaining symmetry. And that's really the important piece to remember. So even if you have a piece of coax that has a PL239 connector, is it 239 PL259? Anyhow, it has a coaxial connect UHF, we'll call it that, connector on the end of it. Don't really get wrapped around the axle around the construction. So it says that this term only applies to the function of energy transfer, not how the device is constructed. What you're really paying attention to is the removal of that current, so your signal is then balanced as it passes out the other side. And here they use a word, common mode choke. For example, can perform the balun function by putting impedance in the path of the common mode currents. And then the load terminals, such as the antenna feed point, and therefore is a balun. So like I was saying, a lot of folks will get upset if you call it a balun or if you call it a choke. So I try to just call it a balun choke. This goes on and on a little bit, but this one here, it talks a little bit about some of the drama or the chaos that gets created by common mode current. And talks about noise being picked up here. You can see that in the feed line as common mode current signals radiated by the current on the feed line can cause interference to appliances and other electronics if they are near a feed line. And so I don't know if anybody here has experienced it, but Christmas time is always a problem, because if I'm operating and we have the Christmas lights outside, my wife comes running up. What happened? What happened? The Christmas lights went out. Or I've tripped plenty of those GFI, the ground fault isolators, on my power outlets in the house and stuff like that. So I do think it's important to use these devices to kind of minimize that disruption. And then this is the last one. I'm just going to go through it pretty quick. But again, here's the sighting if you have the antenna book. And if you don't, I would encourage you to get it. I'm not trying to shill for the league, but the antenna book is really a fantastic resource. But it just reiterates that they're to reduce the common mode feed line current, the chokes create a high impedance in the current's path. It's placed at the junction, the coaxial feed line and the load, such as the antenna, and the choke becomes a choke balun between the unbalanced feed line and the balanced load as an antenna. So there's a couple things I wanted to talk about, is that even if you build a balanced antenna, it's unbalanced, right? Because unless you're cutting that coax in a NIST calibrated lab and you're putting the same amount of solder on all your connections and your crimps are exactly perfect on all of those, they're going to be off. And we're going to talk a little bit about how the feed point location on the actual antenna changes and changes your impedance and also increases the likelihood of common mode current. Um, we'll keep going down. So here's a picture that I took of just some toroids. And I did want to talk a little bit about these because a lot of people have questions around, well, what kind should I buy? And how do I know if I got a good one? And what's the sizing? And so here you have a couple that look like they're made of metal, right? And it's actually like a couple of different, I think there's zinc and magnesium mixes. And those are ferrite toroids. And they're typically, when you look at the name of them, they'll have an FT designation at the beginning. And the bigger ones are an FT 240. And that 240 means 2.4 inches in diameter across the outside of that toroid. So that's how that naming convention works. And then you would have a mix identifier after that. And so these could be mix 31 or 43 or 52. And we'll look at a chart explaining some of that. And then the red and yellow ones are powdered iron toroids. And you use different toroids for different things. Generally speaking, most folks would prefer ferrite toroidal core because it performs better than the powdered iron. If all you got is powdered iron, you can still use them. I have. We'll see some pictures of that, and you just have to make sure that they're tuned or adjusted properly for your use case or your application. The thing I wanted to point out about the powdered iron ones is that they refer to them as a type and not a mix. So like the red one is a type 2, the yellow one is a type 6. When we were talking about the ferrite toroids, it's called a mix. I don't know why they do that. They just do that.
I do have a quick question, Abe. I've heard through the grapevine that the iron core toroids do have better heat permeability. In other words, you can generally push more power through them and not have them heat up as much because they have better permeability. Do you have
Well,
with that?
yeah, yeah. So I think it depends on the application, right? In some cases, you probably want a high permeability. Some cases, you might want a low permeability. They generally, is my understanding, is they don't get hot as much because they don't create the same amount of magnetic flux, I think is the right word, in
Okay.
there.
Yep.
And so there's less energy being absorbed by the core as part of its function. And as a result, you can push more power through them for a longer duration.
Oh, thank you.
Yep. So there's a link in here, Palomar Engineers, and all you have to really do is Google ferrite mix selection Palomar Engineers, and it'll take you to this page. But it talks a little bit about the ferrite mix selection and their guidelines, and they talk about right here the two basic ferrite metal groups having a permeability that ranges from 20 to 80 microhenries are the nickel and zinc, and then there's the mix 43, 52, and 61. And they're the manganese zinc mix, and that's the there's a third one, 31, 73, and 52. But anyhow, this is a pretty good article, and the best thing about the article is it actually has this chart in here, and then you can see the different compositions, the mix number, you can see the permeability. But what I always pay attention to is really when I use these toroids, it's either to work as a balun or a choke to suppress common mode current and help me with RFI, or I'm using it as a wideband transformer to transform impedance, like in a 9-to-1 or 49-to-1 on an end-fed half wave. And so I can see right here the ranges that these work in, right? So the reason I always recommend the Mix 31 for any kind of baluns or chokes is because I want to suppress RFI, CMC, and this works from 1 to 300 megahertz. It says really as a wideband transformer, it's really only a 1-to-1, so it's not really the best thing for that. So I try to buy 31s anytime I'm trying to build a balun or a choke. And when I build things like transformers, most of the time I use a Mix 43. That's what we sell with most of our antenna kits at Coffee and Ham Radios. And the reason is those antennas are portable antennas, and they're designed to work from like 40 to 6 meters. And I don't have the biggest backyard, so I pretty much 40 and higher is where I operate. So you can look at a Mix 43, and there are some CMC, some suppression frequencies where it works, 25 to 300. But as a wideband transformer, you can see I can go all the way from 80 to through 6 with not much problem. A lot of folks, when they're starting to operate in 80 and 160, even 60 meters, when they're building transformers, they'll look at things like these 52s or 61s. 73s are typically used for lower frequencies, 40, 60, 80, 160. But I generally will stick to these 43s. If I was building something where I was going to use it lower, then I would look at the 61 probably. Not that I'm hating on any of these. I'm sure plenty of people have plenty of different antenna designs with all these different mixes that work great. Just really talking about my experience. So here's a slide that I put in here really around what is common mode current, but I think at this point we probably covered everything that's here. So what I'd say is if you want to read it, do a screenshot. No, I'm not going to read it. I'll just keep going and get to it. But I think the main thing is this last sentence where I really just talk about it's really searching for that path to ground. It could come in your shack and cause havoc. And here's a couple of other things where I mentioned people might get wrapped around the axle on the second one where, say concur in both balanced and unbalanced transmission lines, but it's more common in unbalanced transmission lines, such as coaxial cable. You're generally safe from common mode current when you're using things like twin line, ladder line, window line, balanced feed line, because each one of those has your differential mode current going different directions. It's really the common mode current that creates that unbalance, that creates that high impedance path. When you're using balanced transmission lines, it's really less of a problem, but I don't think it's a zero-sum game.
Just so everybody knows, I went ahead and sent the deck out to the club. So you'll have copies of all these slides.
Did you, I did send you a second one because the first one had okay.
Yep.
I wonder if I see my typos in there.
Well, they're used to me. I get typos all the time.
All right. And so these are just a couple of schematics, really just to kind of show folks what we're talking about. And some people like to look at schematics. On the left-hand side on both of those, you have the 50 ohm unbalanced connection where you can see your coax come in. Those squiggly lines mean it's an inductor with a certain amount of windings to it. And then on the right-hand side, the one says balanced and the other one says 50 ohms to the antenna. So on the dipole picture I showed you is probably more realistic of the schematic on top because you can see that there's no PL239 connector or on there on the bottom when you have that. So it's probably more typical of the ones that have the coaxial cable wrapped around. But I just wanted to show those. And then there's a website that right here, this VK6YSF. He's got a fantastic website with lots of different diagrams that you can use to build your own stuff. This is a picture that kind of shows so the green means go and the red means stop. So the way the differential mode current is you have some going this direction, left to right, and some going right to left. And it creates balance inside that the core. The red line would be the common mode current. Should have put that on the bottom because that's where the path to ground is. So I have to fix that for next time. But that is what gets attenuated or gets blocked by the impedance because it creates a magnetic field that stops that based off of the unbalanced nature of that. I don't really like to use the word extra current because it's not. I'll say it's redirected current that's going through your particular choke. And then there's a lot of conversation, and this really confused me, was the difference between voltage and current balance. So here's a couple of schematics here, and I didn't know which one I wanted to use. And then I read an article on DX Engineering when they're like, you should use current balance. That's the ones that you want to use. And those examples that I showed earlier are all technically considered current balance, where you have a connection, like a DC connection through. If you check for DC continuity, it would go through your device. If you look at a voltage balance, it works based off of mutual induction, and you wouldn't have DC continuity across those devices. You need AC current going through there to create the magnetic field that passes over to the secondary coil or winding. And what the current balance typically does, it works off of creating impedance that blocks the unbalanced current. What the voltage balance does is it actually balances the voltage between the two conductors. So your voltage might not be exactly what you want it to be, but it'll be spread across both of the conductors equally. And we'll look at some. I think I don't know if I have an actual picture of one. Oh, I do. We'll be able to see it, and you'll get a kind of a better idea of how it works by looking at an actual picture of one. But it basically just splits that voltage. and doesn't quite work as well in terms of blocking or suppressing your common mode current. It really is just, again, balancing voltage. What you really want to do, the reason you would use a balun or the reason you would use a choke is to stop common mode current. So this, I have it labeled typical shack, but this is an early diagram of my shack when I was really getting into HF. And I'll start over on the right-hand side, and I'm left-handed, so we're going to read from right to left. And so what I have here is a depiction of an antenna and some coaxial cable. And I mentioned I put a choke on either end of that cable. So one at the antenna feed point, one where I call it the shack entrance, where the coaxial comes into my tuner. And that's an LGT Pro 102, I think. Anyhow, my tuner has two connections that go into my radio. One is a power cable, and the other one is a control cable. And I did choke that with clip-on beads because I really am serious about stopping this stuff. And if you keep following that path to ground, I have my radio that goes into this MFJ switching power supply. And so I built my own cable to connect the power supply to the radio. And I took a big old 240 mix 31 and I wrapped like 20 wraps around it and I put it in place. And when I did that, that actually made a significant difference on my noise floor. And I also put a toroid choke on my power cable that goes into my AC mains. I also have this Raspberry Pi I used to operate. I loved when Raspberry Pis got famous or popular because I like Linux. But the USB cable that goes between the Raspberry Pi and the radio, I also put a toroid wrap on that. And the power cable that comes out of my Raspberry Pi into my mains power, I put I wrapped that cable around a toroid a bunch of times. And I was mentioning earlier, I really saw significant improvements in my signal to noise ratio, lowered my noise floor, and stopped any of the havoc that I was observing in the ham shack from common mode currents coming into my ham shack. Any questions about any of that?
Yeah, I do. If you use like a gap protector for static, those kind of things, will that help choke some of this stuff down?
So you're talking about like a
Surge suppressor.
yeah, like so I think I have an MFJ one that supposedly doesn't have DC continuity from the input to where you plug it into the wall all the way out.
Yeah.
It would help block common mode current in those cases.
Mm-hmm.
But at the same time, you have to remember, like in the case of that voltage balun that we were looking at, you still would get the mutual induction, between the two cores that roll in there. So, I think that the blocking impedance is probably the right way to go.
Yeah.
When you talk about the gap in there, that's probably better protection from having something run amok and creating a short to ground that could not a short to ground, a different path to ground. Like if you hook like a floating device up or something like that, sometimes they'll look through that.
Cool.
And so, again, here's just a kind of a different visualization of a typical configuration of when I'll set up an antenna system. I really like using end-fed antennas. And I get that there's a lot of pros and cons, and a lot of people focus on the cons, and there's a lot of drama around end-fed wire antennas, but I love them. And so in this case, I just have an inverted L antenna, and you'll have your transformer at the bottom. And I have the squiggly line representing a counterpoise. I'm a huge proponent of a counterpoise. And part of the reason why we have this common mode current problem is that current is looking for a path to ground. And when you give your antenna something like a counterpoise, it's really the ground side of your antenna. So if you have an end fed and you don't use a counterpoise, it's kind of like using a dipole that only has one leg. It'll work, but it'll work better when you have a counterpoise. And a lot of people are like, well, it's just ground. If I'm grounded at the shack, or if I'm grounding in a lightning arrestor, if I'm grounded here, earth ground's really resistive, and a counterpoise is capacitive, right? So it stores energy and then releases energy. Any energy that you have going into an earth ground is resistive, and it gets burned up in that ground. It doesn't make its way back, and it helps that differential mode current work the way differential mode current is supposed to. So my antenna comes into a transformer, and here I have this choke, and then follow the coaxial down to the radio and tuner. I have a choke there as well. Now, in the last picture, I showed how I go overboard with all this stuff, but this is the minimum type of configuration that I would have as a choke on either side of my coaxial cable. Now, if somebody can't, for whatever reason, Definitely choke at the antenna feed point here, but it's a good idea to do it here as well. So I talked a little bit about the nano VNA, and I can't stress how important it is to have some type of tool to be able to measure things, and look at something graphically and understand what's going on in your environment. So this is a picture I took for actually the other presentation I was talking about earlier, and somebody stole it and they put it on a Facebook group. But I'm not mad about it, I guess. I should get something out of that though, right? But this is just a couple of different types and versions of nano VNAs. The first one at the bottom is just what they would call the nano VNA H. And that one I actually purchased. And then based off some video work that I've done, different companies reached out to me and sent me the nano VNA H4. And then this is a nano VNA V2. Depending upon which one you have, different firmwares will do different things on these. If I was going to buy one, I would really look at this Nano VNA H4. I don't have the best eyes. This has a 4-inch screen. It makes it a little bit easier to read. Still around $100 or less. And RNL.com. I'm sure everybody knows RNL. I'm a big fan of supporting the mom and pop ham shops. If we don't, they're going to go away. You can pick those up there.
That's the one I just
But I wanted to
purchased.
show some pictures of actually using these things and how you can test. And pardon having my face in there, but I couldn't find a clean picture of this particular test. But when you build chokes, one of the things I do is I want to test the choking impedance, or get an idea of how much CMC will be suppressed through that. And so what you do is you do an S21 test. And if you look at this nano VNA, you have port 1 and port 2. Different VNAs will call these things different things, but essentially you're pushing a signal out port 1 of a known value and you're running it. You can't see the coax comes down and runs all around the bottom here, and then comes around and goes back into port 2. And the VNA is smart enough to do some math and figure out the difference in the signal it sent versus the difference in the signal it received, and it'll plot it on here. And so you look at this in terms of dB or dBm is dBm is a decibel in result in reference to a millivolt of energy. And so what you do is you take the center conductor side. So what the coaxial cable I have comes off here is actually alligator clips on the end. They're test leads, pretty common. Most of you probably have them. And then I just ran the center pin side through the red wire that I have on here. And what that does is that it's creating an unbalanced current, because you can see the shield side, the black wire, is not connected to anything. And I've shorted these alligator clips together. So what I was able to do is I was able to make or generate an unbalanced current, feed it through here, and then using the nano VNA scale here, I can measure the loss that I'm getting. That will help me approximate how much suppression that I'm getting. People typically say, hey, a good amount is 25 dB. 30, 35 is really good. I can't quite read what these are. I think that would be 10, 15, 20, 30. So it's about 30 dB down with this particular winding is pretty effective. And so here's another antenna that I was working on. We at Coffee Ham Radio's actually made an antenna that does use a powdered iron core, and this is a non-standard powdered iron core. This is a type 52. It's not, don't confuse it with the mix 52 ferrite. And a lot of people were giving us some grief about this, but the antenna and the core actually worked really, really well. But when I was testing it, this is a 4-to-1 voltage UnUns, and we'll talk a little bit more about these. But the way that I wanted to test this is I said, well, hey, if I'm feeding it a certain amount of impedance, 50 ohm system impedance coming out of my nano VNA through this device into the toroid, I want to be able to make sure that it transforms that to 200 ohms, because that's what I want on the other side. I want a 4-to-1. So what I do is I take two low inductive resistors and I wire them in series. These are each 100 ohm resistors. And then you can see the SWR plot, whatever this frequency is. Like it's 20 meters, this is a 20 meter band. It's like a 1.02, or I can't quite read it, 1.12 maybe. And so I have a relatively low SWR, and it's doing the thing, right? It's transforming the impedance at the ratio that I expect. So I'm happy with that. So this is one way that you can test these without having to put them into the box, your Balun box or whatever. you can test as you go during a particular build.
That's the one you built for the Rybakov, right?
It
Or
is.
Poseidon.
It is.
Okay.
And then here's the Poseidon, the Rybakov-esque type antenna. And I'm doing a pretty similar thing here, except for I'm feeding it the other direction. Now, when you put these, I have a video on how to use I call Yankee test leads, and how to calibrate those out. But what I'm doing here is I'm actually testing this the reverse direction. So on the BNC input here, this is a 50 ohm load. So in the event that you don't have the ability to use resistors, I'm sure you all have a pile of them sitting around. So I just put this 50 ohm standard or 50 ohm load on here, and I test it the other direction. And so my system impedance going here is 200, and then it has 50 on this side, so I should see a 4-to-1 SWR, and that would know that it works bidirectionally. So I thought that was pretty handy. This is one of our coffee and ham radio antennas. These are not to plug too much, but these are a really nice frame. They're made out of a nylon that we get. It's like a fused nylon. It looks like 3D printing, but it's really like an injection spray of this nylon, and they're really durable. Really, really love those. I use them for everything now. And the other thing I want to show is that one of the tests that we like to do is test transformer efficiency. So you would say, well, how much loss am I getting in this core? Because a lot of people say, well, I don't use NFEDs. I don't use transformers because they're very lossy, and I don't want any loss. These are 9-to-1 UnUns that I wrapped around the Type 2. I think these are 120s, powdered iron toroids. And what we do is a measurement similar to the one of the ones that we looked at earlier, where in this case, this VNA calls it channel 0 and channel 1. So we have a signal coming out channel 0. It's going to go through this mess and then back into channel 1, and it'll compare the output signal to the input signal. And what I do is I just connect these like I would a normal antenna to a termination that I'll connect coaxial to. And then I take the aerial wire. So this is what would be my element. And I connect it to the element wire of the second core. And then I'll shoot short the ground out between the two of these. And so when I run these, I'll get a certain amount of loss. And what I do is you take that loss in dB. So say in this example, it's 3 dB of loss. Just divide it by 2, so it's 1.5 dB of loss through that core. It's actually much lower than that. Well, it might be higher at certain frequencies, but that allows me to understand about what percentage of my power will get lost in this core. And then depending upon the core composition, I can think about things like, is this, the right material? Is it going to be able to handle that? Is that amount of loss acceptable to me or not? But this is a really handy trick to be able to measure core efficiency. The thing is that the two cores that you're measuring have to be similar. So you can't take like a PAR NFED box and connect it to one of these and divide by 2, because they're going to perform differently and they're going to have different composition. The other thing is that no two cores are going to perform exactly the same. So dividing by 2 gives you an approximation or a good guess. And some folks will ask this question around, hey, well, what's the difference between the Balun and the UnUns? And so with the Balun, what you want to do is you want to be able to attenuate some of that common mode current, but they don't do it well. You're really better off using a choke. So a lot of times what you see is companies now selling something they call a hybrid Balun. And really what it is a 4-to-1 and then a 1-to-1 choke behind it. It's two devices baked into one. Palomar Engineer sells one that's super popular with people building like Delta loops and stuff like that. But on each one of these, I have the shield side marked in silver. I did that with a silver Sharpie. If you don't have a silver Sharpie, it's a fantastic investment for your ham shack. And with the way that these, and we'll look at a schematic for these, but the way that these work is you have a number of wraps. In this case, it's 8. And then we take the center ones, we tie them together, and that becomes a connection on the Balun that goes to ground. So you have a direct connection to ground. Our center connection here goes into the hot side. And that's really the only difference between a Balun and an UnUns. When people say, well, what's the difference? It's that, do you have a direct connection to ground or not from the center? So if you take a look at, and I had that completely backwards, I apologize. The UnUns is the one with the direct connection to ground. So here's the schematic. So you can see that we have a primary here, and then this is our secondary on this side. Halfway through for the Balun, we have, I did say that right. We do have our connection right here to ground. And on the UnUns side, and here's the UnUns with a direct connection to ground. So on the balance side, what you do is you have your signal that comes through either one of these sides, and hope when it's seeking that low impedance path to ground, they're just going to have to traverse through some of this mess and reduce your common mode current a little bit. So I wanted to, are we doing all right on time, John?
Yeah, you're doing fine. No worries at all.
All right. So I wanted to talk a little bit about antennas and how we look at designing them and some transformer stuff to kind of make this all applicable to your everyday life. So in this case, we have a 66-foot dipole antenna. So it's really designed for a 7 megahertz signal or 40-meter band. And I'm sure most folks know that at your feed point here in the center is where you have your high current and your low voltage. And as you move towards the ends, your voltage gets higher and the amount of current you have on the wire gets a little bit lower. Now, I mentioned earlier that I was a greedy ham and I'd love to set a 40-meter dipole, but I want to get multiple bands out of that. One of the challenges that we have is that when you move your feed point either left or right, you increase your impedance. It gets away from really a dipole at a half a wavelength above ground that's perfectly cut is around 72 to 73 ohms. But as you move this feed point over, you increase your impedance and you get more and more CMC prone. And the reason you get more CMC prone is that you're increasing your impedance and your ground currents are looking for a path to ground, and it's easier to go down the coax than it is to go to your ground side of your antenna. This is that same antenna if you were putting a 20-meter signal into that, right? So you have like the super high impedance here. You'll have a little bit of a lower current and you'll have higher voltage here, and that messes with your impedance. But you can see you have two higher sources of current here and here. You're kind of dividing that. And then if we add 10 meters into that equation, you have 4 cycles of that because of the way, 20 is a halfway. 20 is half of a wave of 40, and then 10 is 4 times. Can I say that right? Yeah, I think you get the drift.
Yeah, you got
it.
it.
When we look at this schematic here, what we see is that we can see right here, there's a really predictable point of impedance where our currents for all of these bands, 40, 20, and 10 is the same. So you would have the same impedance at this particular feed point. And that's how the concept of all center fed dipoles comes up. And I'm a pretty big fan of all center fed dipoles because it meets my criteria of being able to get multi-bands. So what we try to do is we try to design a transformer that'll transform this particular impedance ratio, right? And that way I should be able to get, not perfectly, but I should be able to get these 4 different bands on this particular antenna. So when you move this down, a lot of people will argue and say, well, which is the best place to feed this? Like maybe I want to feed it here, and that's a little bit of a compromise, and I can get 15 meters on there. But in this particular scenario, we're looking at feeding it at around 33%. And I believe 33% is 200 ohms, right? And then if you get the further down you go all the way to the end is 2,450 ohms. Somewhere right around here at 75% and 25%. Some folks recommend using a 9-to-1, but you really are ending up using kind of like a random wire antenna at that point. But so if we're going to feed this here, we want to come up with a transformer that works, and that's where 4-to-1 comes in. You have about 200 ohms of impedance. A 4-to-1 will get you to a 50 ohm transmission line. I wanted to talk a little bit about a doublet, and I'm sure folks use these. They're very popular antenna where you have kind of like a dipole that's fed by twin line. And people might want to argue that, hey, well, that's not really a doublet if it's not twin line all the way back to your tuner. So maybe this is a G5RV or something like that. But a question I get asked a lot is that what kind of transformer should I put here? Should it be a 4-to-1 or should it be a 1-to-1? I think the general consensus for years was that you want to put a 4-to-1 here. But I think that tide's changing to actually you want to put a 1-to-1 here because a lot of times your impedance actually might be lower. Like you might have 150 ohms of impedance based off of your antenna system, your twin line, and your dipole. Or you might even have 75 ohms, for example. And if you put a 4-to-1 here, that's going to pull that down to about 18 or 17 and a half ohms coming into your coaxial cable, which could be a little bit of a challenge for your tuner to tune. So a lot of folks are actually putting one-to-one choking balance here and then letting their tuner sort out the impedance nightmare. So if your antenna says 500 ohms, a one-to-one here would still present 500 ohms on the other side. But this is a voltage on in the box. And I wanted to talk a little bit about project box construction. One of the things is that these toroids, they do get hot because we are pushing energy through them. So what I like to do is keep the toroid raised off the bottom of the box. Now, a lot of times with commercial units, you'll see these things glued to the box, or you'll see a bunch of epoxy around them. And all that epoxy does is prohibits that thing from breathing and kind of getting circulation in there. So I like to use these boxes with a raised floor because it gives me a little bit of air gap in there to deal with some of that heat. The other thing I wanted to mention here is this box has actually got a vent on there. And what that vent does is if I'm using this box in the wintertime when it's cold and I'm heating it up, I might get condensation, and this vent will allow some of that condensation to evaporate at some point and reduce the risk of corrosion inside the box. But it also will let out heat in the event that there's heat pressure in this box. It'll force its way out of there. But lots of different companies make different types of project boxes. This is just one I happen to pick up and be pretty happy with. And this is, it's 4-to-1 voltage on. This is a 49-to-1 voltage on that I made, and this is based in a 3D printed box. This is an antenna I built years ago, and it's a smaller. It's the T140 mix 43 toroid. And I wanted to talk a little bit about the composition of this one because the 49-to-1s are a little bit different. So we talked a little bit about primary and secondary windings, and when I built this, it was a real head scratcher for me, and I did a video on it. And a lot of people came back, and the thing is that this twisted primary, one wire comes out of my center conductor on my BNC connector here, and it loops around and it comes right back down into the ground. And so you would say, well, hey, that's a DC short. How does that work? It shouldn't work right. And then my secondary winding starts at this ground and wraps all the way around 14 times and then runs to my antenna connection point, which is the wing nut on the left. My counterpoise is the wing nut on the right. So you would call this a auto transformer because if you touch the shield or the ground side of this and you touch your element connection here, you're going to have DC continuity through. So that's referred to as an auto transformer. The fact that it's got a DC short through it shouldn't make you worry too much because we use AC current and RF, which behaves a little bit differently. So when we have a signal coming in through this BNC connector, it does create a magnetic, electromagnetic coupling with the secondary winding, and that's how your energy gets transferred out of this element. The other thing that's unique about these 49-to-1s is that you do get some capacitance with the coupling that takes place here. And one of the things that they do is they actually put a capacitor on they also short these out with a capacitor. It's not really a short, but they connect these together with a capacitor, and that lowers your SWR on higher bands. So for this one, I made it, it's for 40 meters. So I put about a 66-foot element on here, and my SWR started to creep up as I got closer and closer to 10 meters. And what I did is I put the capacitor on here. In this case, it's 100 picofarad, and it started to pull that down in the higher bands. Some people will argue and say, well, you should have 120 picofarads or it should be 150. If you're going to build your own and you're having problems, I'd start with 100. And then if it doesn't work right, then I would work on modifying from there. The thing that's funny is that the league, and I'm a big proponent of the league, in the book, it says to use 120 picofarad capacitor, but the ARRL antenna kit is 100 picofarad capacitor that comes with it. So it's just like ham radio. There's a bunch of disagreement all along. So I wanted to put these two diagrams up here. They're really popular, and you see them all over the internet. Talking about 49-to-1s. And there's even a little bit of misinformation in these. Like this one this is actually the diagram that I used to build the one that we just looked at on the previous slide. And it says 49-to-1 transformer. And then here it says 49-to-1 auto transformer. And people will make the argument that the auto transformer, because it's a single wire that's tapped right here at the center conductor on your coax, that's what makes it an auto transformer. I could be wrong, but my understanding is auto transformer means you have DC continuity from the primary to the secondary, which you do here. And you could also make an argument that this one is a single piece of wire because they're both connected at the ground and they just happen to be twisted and folded back on themselves here. I don't really care about all that. These 49-to-1 auto transformers, as they're called, have become super popular. In YouTube videos, people have shown that they've have better efficiency than the 49-to-1s wound this way. And in some cases they do, but the one on the left actually takes advantage of the whole core. And these things do become a little sensitive to heat. So your core can actually fail under two different conditions. A lot of times folks will get those confused. So it can reach what's called its Curry point. And that means that it hits a temperature at which it stops being ferrous and it loses its ability to build a magnetic field around it. And so when that happens, all of your magic that takes place goes away. Your SWR is going to go shooting through the roof and you're not going to be transforming impedance and you're going to have problems. That's what happens when you hit your Curry temperature. So the one on the left spreads the heat around because the heat comes off of each one of these windings. The one on the right doesn't. It concentrates all that heat. So if you look at these under like a FLIR or something like a temperature gun, what you're going to see is you're going to see extreme heat in this one part of the core. If the core gets too hot, it can actually crack or fracture. Here you'll see heat, but it's distributed evenly across the core. I think it's probably a good idea to have it distributed a little bit more across the core. The other thing is that your core can become saturated, which means that it's become as magnetic as it can possibly come. And so what'll happen is that your antenna won't perform the way you want it to because it needs more EMI or it needs more electromagnetic coupling, and it's not getting that because you're at a saturation point. And now that saturation point can make the core hot and can cause you to drive towards a Curry temperature. But they're two different failures that folks definitely conflate. Anyhow, I don't really have if yes.
Hey, you were talking between transformer and auto transformer. The real difference is with the transformer, you have two sets of windings. The auto transformer, you have one winding that's tapped. And that would be your difference between an auto transformer and a transformer.
Thanks, John. I do appreciate that.
Yeah.
When we were having the great debate on the internet about it, the thing was is that these two wires are connected here. So is it a single or a double winding? Again, I do definitely appreciate it. I don't care one way or another. I do have antennas that I've made with a 40-to-1 where I don't have I have these windings close together, but I don't have them twisted. And I also don't have the connection to ground on my secondary. So it looks a lot more like the voltage on that I was showing earlier, the schematic that I was showing earlier. So it just uses induction to get across. The challenge with those, and that's the way that they used to build antennas in the old days, is my understanding, is that you get static buildup on your antenna because it doesn't have a path to ground. So when you get that static buildup on there, you can start to have some other problems. But I think that was everything I was going to cover on these two particular slides. I was going to say, if you built this one on the right, I wouldn't shame you. I would say, awesome, you did a great job, and they work really well. And I know a lot of people have a lot of success with them. It really just boils down to a preference where I kind of prefer this one right here. And here's just a couple examples of some 9-to-1 UnUns that I built. I actually did a video on the one on the left. It was super popular. I get tons of questions about it. But this one has a primary and a secondary like all the other ones, a certain amount of windings. I used stranded wire here because a stranded wire gives me a little bit more surface area for RF to pass. And the thing about these 9-to-1s is that they call them random wire antennas, but the measurement of your element has to be a specific length where it's not resonant on any of the ham frequencies. So it's not really quite so random. The one on this side is the Cartena Aries, which is a 9-to-1 DIY kit. But we use this one for portable, where the frame also doubles as a wire winder. And we're starting to get to the end. I did want to put it. This is the 4-to-1 that I was using earlier, and I just wanted to kind of put a little chart in here talking a little bit about the math behind it, because a lot of people, ask the question of how it works. And so really it's all based off the ratio of your turns on these. And so what we would say N is equal to our turns ratio which would be the number of windings on the secondary divided by the number of windings on the primary. So if you take a look at this, we have 16 turns on our secondary and 8 on our primary. So you get N equals 16 divided by 8, which is 2. So our turns ratio is equal to 2. And then we have this thing called our primary impedance, Z1, because Z is the symbol for impedance, P being primary, and then we have our secondary, ZS. So ZS is really equal to the number of turns squared times our primary impedance. So in this case, our number of our turns ratio is 2 squared times 2. And then that what that gives us is 4, right? So 4 times 50 gives us our 200 ohms. And I think I might have a typo here on the second formula because our Z primary.
Yeah,
should be
Z
50.
primary should be 50. Yeah.
Yeah, so I should have fixed that when I was going through this last night, making my edits. So there's a little bit of an error there. And then this is a little bit more where people will say, well, how does that actually work? The way I always explain it to folks is that if you have like let's say you have like a 49-to-1, for example, the ratio is you have 14, like if I go back up here. So this one has 14 total turns. You have 2 on your primary, 14 on your secondary. So if you do that same math, you take your 14, you divide it by 2, and you get 7. 7 squared is 49, right? So that's how you get that impedance ratio. And that's the same thing over here. In the example I did here, I did it on a 4-to-1 because the math's a little bit easier. You get the 2 and you square it, gives you your 4. 4 times your primary impedance gives you your 200 ohms. But if for the folks that really want to get deep into it, if you take a look at Ohm's law, you get voltage equals current times resistance, where you can remove resistance on the other side and you get resistance equals voltage divided by current. We substitute R for Z because we're talking about AC impedance, not DC resistance. You get Z equals voltage divided by your current. And then what we would do is we would take the number of turns on our secondary, number of turns on our primary, and get that same turns ratio, number 2. So voltage on the secondary is equal to 2 times your voltage on the primary. Your current on the secondary is equal to the voltage on the primary divided by 2. And then if you just go through the math, you get to your 200 ohms impedance. And that's the end of the stuff. So it's
Cool.
about an hour and 8 minutes. I ran over a little bit, so I apologize.
That's
Awesome
all right.
presentation, Abe.
Yeah.
Man.
Really good.
Yeah.
Well, thank you. I appreciate that. I tried.
Anybody have
a
any
question.
questions?
I have a question.
Go ahead, Danny.
On your wire between your power supply and your radio, you put a choke. How many turns, and are you using a 31 or 43? Can you describe that choke?
I'm using 31, and I used a T240, so it was a little bit larger. And I used 10 gauge wire, if I remember correctly. And I was able to start on one side and just keep going all the way around. And I believe I got about 20 turns on that.
Wow. All right.
So I do
Wire
have
size, does wire size affect these Baluns?
No, I think wire size really, the biggest challenge with wire size is how much surface area and RF you can push through there. And also, you come up with a resistance, like smaller wire sometimes gets a little hotter faster if you have something in there. I typically err on the side of heavier gauge wire. And I don't know if that's dramatic or not, but like on that 49-to-1, I use 16 gauge wire, and I have internet know-it-alls that come up to me and are like, you really could be using 22 gauge wire on there. And I just err on the side of heavier, beefier, and I'm not doing a soda to operate CW with my 49-to-1. So to me, it's okay if it's a little heavier. No offense to soda mountain climbers.
I agree with over engineering. That's the way to go.
Right.
Any other questions? Wow. Okay. Well, you did a great job, Abe. Thanks so much for this. We do appreciate it. Brian,
anytime.
I think, Brian, do you have a question?
Yeah, sorry. I was just going to ask, first of all, thank you. And thanks for all those videos you do on the nano VNAs. Those are great.
Good.
It's nice to have someone show you how to use that to actually be able to use one. But I think you said you didn't like the iron powder core.
Oh, no, I like them. I've show you, I got a giant bag of them just the other day. I love them. Can't get enough of them. It's just that they tend to sometimes not have the same broadband capabilities as the ferrotoroids.
Yeah. I documented ham radio dudes, whatever he's calling it, the dude tenna, and he's using an iron core, sorry, powered, god damn it, powdered iron core, toroid in there, and it does bring the like after you have to put a little coil in the end fed at about 8 feet to bring down the frequency of basically anything above 20 meters, because it does throw off the frequency above or below 20 meters. And so in the case of an end fed,
no, I'm familiar with folks who will put those coils there. I actually put a coil at the end of mine, and that allows me to shorten its overall length. I have a 40 meter, what did you call 40 meter end fed halfway, that's about 42 feet long as opposed to 66 feet. I call it the shorty 40, not to be confused with the sporty 40 that Wolf River Coils puts out. But
nice.
But yeah, there's challenges to things. I typically these days try to use like powdered iron cores for stuff. If I'm building like here's a 20-meter bandpass filter. It's not going to show up so well because of my green screen that I built, but you can see that's powdered iron in there. But they tend to be a little bit higher Q. Like I said, less bandwidth. For most antenna stuff, I prefer to use the wider banded stuff. And if you're going to use an antenna tuner or something like that, then I guess you could probably get away more with the powdered iron. But it's just really application specific.
Have any other questions?
You knew I wasn't going to let you get out of here, Ape, without asking a question, right?
That's right, Andy.
All right. So you got your 240 here. Now, I also have one of these big ones that I know you're supposed to put on like your refrigerator, or you're supposed to put on your dryer or something like that. This is a Mix 31. So
these things.
Yeah, there you go, right there. So you ever wrapped a bunch of coax around here and see what happens? I mean, could you use this as a choke?
Is that Olive Oil's hula hoop?
Yes. So this is a TFT 400, so it's a 4-inch diameter.
That's the comparison there between the 240.
Yeah, well, the reason this one's so big and that it's so popular is because you can get that fat plug on your dryer or your washer through that and get your multiple windings on it. So I had a refrigerator that created RF in my house, and it was brutal. And so that's what I used to use this one, was the refrigerator. Refrigerator stopped working, so now I have the core here. I think I've got another one somewhere, but these are a little bit more expensive. They're about $40. But like I said, I'm serious about battling that RF and CMC, so I put them on everything. You could make an antenna with this if that's what you were getting at, Andy.
A choke.
Yeah, you could do that. But the thing is that like when you're using a core as a transformer, like a 9-to-1, 4-to-1, 49-to-1, 56, whatever it is, the transformation takes more energy, and your cores get hotter. When you're choking, the common mode current is generally a low amount of current, so you can get away with a lot smaller core for that. You don't have to use a giant, massive core.
Well, any other questions? All right. Well, Mr. Ape, thank you so very much. Wonderful job and extremely informative. And,
well, thanks. I appreciate you having me, and definitely enjoyed it.
Well, you did a great job, and we'll have this up on YouTube, probably on our channel, probably by the end of the weekend. So
I was hoping by the end of the evening, John. Well, I'm just kidding.
I got a little bit of editing to do, and I have to redo my introduction, so because I screwed that up.
Thank you, and I'm going to get out of here because I've got the bladder of a 6-year-old girl, and I really got to go. So thanks everybody. It's great
brother.
meeting you, and thanks for the hospitality.
Thanks, Abe.
Take care.
Thanks,
Take
Abe.
care.